Today, we're going to be talking about a project I've been working on for about 6 months in my free time. It's been an especially difficult project for me because I don't have a computer science background, and it's kind of important for this project because the goal is to make updating filtered lists logarithmic, which could have the potential to significantly speed up your applications, depending on how often you're filtering lists, right? This is to do MVC. I'm sure a bunch of you recognize it. It's the simplest app you could possibly build, right? So we claim. We're going to make this app, well, not this app, but we're going to make the most commonly used utility in this app and the most commonly implemented feature across a wide range of apps, something that's so common it's even in the to-do MVC app. We're going to make it go from scaling like this, which is linear, to something like this, which is logarithmic. It's very exciting stuff. So here's how we're going to do it. First, we're going to examine a naive filter by feature implementation. We're just going to do it as stupidly as we can. We're not going to rely on any tools. We're not even writing code, but we're just going to do it in like as if we were just writing in jQuery and we didn't know any better. We're going to improve the performance of this implementation using a small diffing algorithm, and then we're going to kind of try and gauge how that's going to scale over time. And then we're also going to take a tour of our logarithmic filter algorithm that I've been working on for 6 months. At the very end, hopefully we'll have time to actually demo our implementation. So that's cool. Let's get started. So in order to help visualize how the arrays are being filtered and how memory is being moved around and whatnot, I came up with this kind of like template. The goal of the template is to kind of give us an understanding of where we're spending the most time and how it's changing as we go from the original update of a filtered list to the update of our DOM. So on the left here, you see we have this kind of like object land section. Operations that occur here cost 1 unit of time. On the right, you'll see there's DOM land. Operations that occur there cost 10 units of time. It's mostly arbitrary. It's just chosen for the sake of argument. Inside of object land, you'll notice we have kind of two columns there. One of them is our to-dos list. This would be like your just raw list of all of the to-dos in an app like To-Do MVC. This is the unfiltered list of to-dos. And then the second column being completed, this is our filtered list of completed to-dos. So only to-dos that are completed will wind up in this list. And then finally, on the far right, in DOM land, there's a node list. And this is what would be in the browser representing the completed version of the to-do list. Right, yes. Cool. Most importantly, in the bottom right, you'll notice there's this little cost counter. So as we start to conduct operations on these lists and this DOM, we're going to kind of keep track of what it's costing us in order to do so. Cool. So let's get started. Oh, also one quick note. We're going to start from this point, right? We're going to start with an existing list of to-dos. We're assuming we already have it like in memory. We don't have to go do some async request and build it. And then we're also going to start with its filtered counterpart, the completed list, right? So we already know that these two items will be filtered out of the main to-dos list. And then we're also going to start with our rendered DOM elements already. And the reason we're doing it like this is because everything that happened before this can't be optimized. It just is what it is, and I just hope that you all trust me on that. Let's see. So we're going to update this list on the left, to-dos, by adding a new item to it called run. So now we have hop, skip, and jump, and run. Skip is the only one that's not completed. By adding this run element or item to the to-dos list, we really have to refilter completed, right? So what we'll first have to do is discard all the elements in completed, and then afterwards we can start filtering through the unfiltered to-dos list. So it looks something like this. First, we'll hit hop. Hop is completed, so we'll copy it over to the completed list. Skip is not completed, so it will not be copied over. Jump is, run is. You notice the cost is going up every time we have that little red circle touch one of these elements in the list. So now we have our completed to-dos list. Everything's been filtered, and this is, we're halfway there to getting what we wanted. We just got to get it into the DOM. But we already have a couple items in the DOM, so we're going to have to empty it. That's kind of expensive. We just noticed on the bottom right there, we increased 20 units because there's 2 items in there. We removed those 2 items. It's 10 units per operation, so we're up to 20 units just for that one little thing. It's kind of expensive, but hey, we're just building a filtered list. We don't really care about performance right now. So now we can start rebuilding that DOM list to represent the completed list. So we'll start iterating that. And then as we do, we'll add those elements to the node list. And it looks something like that. Altogether, over the course of this entire updating of the filtered list, of the to-dos list and rendering the filtered variation, we somehow got up to 55 units of cost. So this is our baseline. All we have to do is really improve upon that. And I noticed some wasteful stuff while we were doing that. I think we can probably pretty easily drop it down some. So the first thing that I noticed is that when we were refiltering the completed list, after the to-dos, like the run to-do was added, we unnecessarily removed these 2 items, hop and jump, because we were kind of starting over from scratch, right? And that wasn't really necessary because we had to go back to the original to-dos list and reevaluate each of those and then put them right back where they were. So there was no real change from the time that they were first there when we started updating the to-dos list and after we've updated the to-dos list. So really all that changed in the end was that we're going to add a run element to the end of the completed list. But in doing that, it cost us 3 units, which maybe not too bad, but it's something. The next thing we noticed is that when we were rebuilding the node list and we were updating the node list to represent our new completed list, we had to, like I said, invest 20 units just to empty the thing out and start over. That was really expensive. But then also putting the items back in was really expensive, 20 units per. And again, these elements didn't change. We took them out, we put them back in, and they're exactly the same after. So it was kind of unnecessary. If we hadn't touched them at all, everything would have just been fine. But we did, and so it cost us. If you were to kind of break down what we thought was necessary and not necessary, what you'll find is that 12 of the units were absolutely necessary, and 43 of those units we just invested were completely unnecessary. That's very, very, very inefficient. So we know of a way to improve upon this, right? We've seen diffing algorithms kind of speed things up by moving some of the computation over into object land instead, right? This is the kind of thing we want. We just want to know what changed, and then once we know what changed, then we can just update the DOM as efficiently as possible. So let's give it a run, right? So we're going to go back to the beginning. We're going to update the to-do list, right? Add that run item. In doing that, we're going to filter the to-dos, right? We got to update that filtered list. But this time, instead of just dumping the completed list and starting from scratch, we're going to save a reference to the completed list. We're going to call it previous completed. I ran out of space there. Then we could kind of discard the completed list and start rebuilding or refiltering from the to-dos list. All right, so we'll hit hop again. Hop is included. Skip is not. Jump is. Run is. Excellent. So now we have our new completed list. We have a reference to our old completed list. Now we can actually start doing some diffing and hopefully update the DOM much faster, or in total spend less units accomplishing the same task, right? So let's begin with the diff. It's really simple. We're just going to traverse the lists together simultaneously. We're going to visit each of the items. So first we're going to visit the first item in completed and the first item in the previous completed, and we're going to compare them to see if they're the same. If they're the same, cool, we can keep on going. Jump and jump, again, the same. Nothing needs to be done here. This is where we get to run. Run is new, and in our previous completed list, we did not have that. So this is, a change that we have to actually apply. So we're going to patch the node list with this change. So just to get there, we're up to like 8 units. Not bad, but we haven't done anything in DOM land, so we're doing pretty good. Let's update the DOM with the new item, the run item, which the diff informed us we need to move over. 10 units. We knew we were going to have to do that. No big deal. And here we are. We've accomplished the same thing, and we're at 18 units, which is a huge improvement over what we previously did. We can see here. Now what we see is that we only had about 6 units of wasted effort, right? Because 12 was what we absolutely needed to move to update the to-do list, and then to move that node into a filtered list, and then to move that filtered item into our DOM nodes, our node list. So the question, though, is, did our solution that we just implemented scale, right? Can we rely on this being like ultra fast and performant, even when we're, doing hundreds of thousands of items, if that were the case, if our browsers could handle that kind of stuff? So we're going to scale the example up entirely. Instead of 3 initial items, we'll have 30 initial items. And instead of 1 of those items not being complete, there'll be 10 of those items that aren't complete. Similarly, instead of doing 1 update, we're going to do 10 updates, right? So if we go through this, and I don't diagram it all out for you, I just do some little math on a notepad here, and we come to this conclusion. We find out that if we were doing that many items, we are wasting 600 units of work, not really accomplishing anything. The only really important things that actually mattered, that could not go without, were these 120 operations. So it's like super inefficient, and there's room for improvement there, right? So we can keep on going. Ideally, we would do something else. Let's take a look at what the ideal approach would look like. So now we're going to go through this whole process again. We're going to add the run item to the to-dos list. Something is going to happen. We don't know what, but it's going to be probably more efficient. We want it to be more efficient anyway. And we're somehow going to be able to tell that, hey, we should move this one item in the to-dos list over into the completed list. Cool, and that would only cost us 1 unit. That'd be great if we can figure that out really quickly. Then we want to do it again, basically, right? We want to, in some way, shape, or form, figure out how we can update the node list in DOM land without a whole lot of overhead and get our fantastic result. And that would only cost us 12 units. Like, we can't really make it any faster than that, right? We just copied the exact item over. But it's not really like that simple, right? We can't just copy that one item over and say, hey, it was that easy, because it's really not trivial. The run item was added to the to-dos list here, but we don't really know at what index we should put it in the completed list. We can do some work to figure it out, but then again, we're just doing more work, right? Like, we're not gaining anything. We're just changing the style of work, maybe. Instead of refiltering the list, we're just going to iterate and search through the completed list and find an insertion point. That's not saving us anything. We still have to do that work. And if it seems like, maybe I'm overcomplicating it, try really quickly to figure out where this item belongs in its filter variation. It's not super obvious. I mean, you can figure it out, but it's going to take you a couple seconds. And if I have to write a program to do the same amount of work, it's also going to be inefficient, right? Okay, so this is where I decided to get clever. We have to think outside of the array brackets and or box. After many failed attempts and a bunch of help from my coworkers, I learned that no matter how I try to work with these arrays, I'm not going to be able to update them quickly or efficiently. But if we look at RedBlack binary trees, they offer a couple of properties that we can maybe take advantage of. And I'm not sure if any of you guys are aware of how these work or remember how they work. For me, I had to learn them, so they're fresh on my mind, but I'll give you a quick run through on how they work. So first we add like the first item in our to-dos list into the tree, and this becomes a root node. Next, we try to add the next item. The next item would be skip. It had an index of 1. So we'll compare this new item we're putting into the tree against the root node, and you see here that skip has a value of 1 because that's its index in the to-do list, and then hop has an index of 0, so 1 versus 0. We need to put skip to the right of hop. So that's what the tree does. That's fantastic. Now what happens is we want to put in this third item, right? And so jump tries to go in. It's got an index of 2. Hop's got an index of 0. We compare them. And then the cool thing about the tree is that it basically does the same exact operation, but on the next node and the next node and the next node until it runs out of places to search to compare nodes, and it just assumes this is where I belong, right? Because I used logic and reasoning to get here. So jump compares itself with skip, and it says I've got to go to the right of that. Fantastic. So one of the beauties of binary trees is that they drastically reduce the cost of operations on them, like insert and remove or find, because you don't have to visit every item in the tree, right? So we can kind of just like split the size of the data set like in half every time we kind of try to find that information, which is super helpful. But in order for that to happen, the RedBlack tree has to balance itself, right? Right now, this is like a three tier tree, or like has a depth of 3 nodes. And so I would have to compare myself against 2 nodes to get to the third one. But if we rebalance and rotate, now the depth is much more shallow, and in order to find a node, I can find it in 1 operation instead of 2, right? And so this is constantly happening as you're adding elements to the tree. It's very efficient, and it's a really clever design. So then the question becomes, how do we use these RedBlack binary trees to filter arrays? Because that's kind of not what they're designed to do initially. So we'll take a look at our model again. This is the algorithm, right? The result of the algorithm, and it comes in a couple different parts, and they're really intricate little bits and pieces. I hope you guys can see it, but I'm going to go walk through it like step by step and kind of show you all the different little moving parts. So this is what it's going to look like when it's done, right? Look on the left, we see we've got the to-dos list. It's already got the run item in it. We've got this thing called the predicate tree. It's in the center area. Below that is a completed tree. And on the right is the node list that we're familiar with. So all we really did was take out this filtered array that was in the center, and we replaced it with these 2 trees. Okay, so let's look at the predicate tree. The predicate tree has 2 primary roles. For every item in the to-dos list, there's going to be a node in the predicate tree. So it like maintains a one-to-one relationship. Obviously, they're structured differently. The to-dos list has like indexes, and they're all one after another, and then this tree has this kind of strange pyramid shape and has no indexes. But that's its job. The predicate tree just makes sure that it has all the same items that the to-dos list has. Also, if you were to be more generic, we would just call that the source list, because this can be applied to any list, obviously. The next thing that it's meant to do is match the order of the to-do list. So if items are moved around or added to the beginning or at the end, it's going to match that too. Like it has to say 100% in sync with both the order, the number of items, so on and so forth. Perfect. The predicate function's nodes, so the squares in, sorry, not the predicate tree, the nodes in the predicate tree hold on to something called the predicate result. The word predicate, I don't know if everybody knows what that means. You'll probably find it in like load dash documentation or underscore documentation. It's the function that you use to compare against each item. So if you said todos.filter function if completed return true, and everything that returns true is going to be in your filtered list, that function that you passed to the filter method, that was your predicate function. It's used to determine if the item should or should not be included. So the predicate tree has the responsibility of holding on to the result of that function. But it also can be made to bind to its source item. right? So if my source item changes, so for instance, if hop got renamed to hopping, that predicate function can rerun and make a decision about how to proceed. So that's kind of a neat thing to do. Cool, we'll keep going. I think that's right. The second tree in our algorithm here is the completed tree. It looks a lot like the predicate tree, except it's missing some nodes. The completed tree contains only nodes associated with items that were filtered from the to-dos, in this case, right? So this tree only has items that we want in our filtered result set. Okay, simple. It's just our filtered list. But it has like this kind of one nuance. It has references to its sister nodes in the predicate tree, right? So you see these little asterisks that I have in each node. That's just meant to represent that any one of these nodes can very easily get access to that predicate tree and potentially traverse it if it wanted to. We'll call those sister nodes. So the nodes of both trees have a couple things in common. They're not 100% unique between the two of them. Each one of the trees' nodes maintains a left count, a right count, and a gap count. And what that means is, if you look at the skip item, kind of to the right of the false, you've got this colon, and you've got 1, pipe 0, pipe 2. So the 1 implies that there's one item to the left of it. The 0 implies that there's no gap to the left of it. So like if you were to create an array where you put an item at 0 index and then you put an item at the 3rd index, you just created a gap in between those two, right? And so using a left count and a left gap count, we can calculate what the index of that node is, right? So with a left count of 1 and no gap, we can easily assume that this node is at the 1st index. But the important thing there is that we didn't have to like store that information. We can calculate it on demand at any time. Another thing that each node has is a reference to its left child. So for instance, skip has a reference to hop. And you can see that kind of through the lines there. And then it has a reference to its right child, assuming it has one. Similar on the right, skip has a reference to jump. And then also, it's able to implement a linked list, a doubly linked list. So this hop, I'm sorry, I don't actually have an example in here, but essentially if you had two leaves that had split apart, right, and then they'd come back together, and the furthest rightmost node in this leaf and the furthest leftmost node in this leaf, they're not actually sharing a child or a parent directly, but we can still relate the two using a linked list, which is just fun. And then the other most important thing is that each one of the nodes in both trees has a reference to its parent. This is super critical because, well, we'll explain later. Let's continue. Actually, I think that's everything. Cool. That's all our prerequisite algorithm teachings. So let's just review real quickly. The predicate tree has the predicate result, the true or false, should this or should this not be included in the resulting filtered list. And then the completed tree has a reference to nodes, sister nodes in the predicate tree. And every one of the nodes within its own tree has a way of linking to other nodes in the tree, for instance, siblings, children, and parents. Cool. So I think we're ready to actually model the solution. So we're going to start with the same place where we started before with the filtered list. To-dos is just got the 3 elements in it, hop, skip, and jump. And then we're going to modify that, right? But in this case, we actually have a little bit more infrastructure built around it. The predicate tree already has those 3 nodes associated with the to-dos items, hop, skip, and jump. And it also has metadata about them with regards to their indexes or their left counts and their gap counts. And then it also has already solved for the predicate result. So we know true, false, and true. Yes, it's yes, hop is completed, skip is not completed, jump is completed. And then finally, not finally, actually, our completed tree has references to the relevant nodes in order to filter the to-dos list, right? So we have the hop node, we have the jump node. They have their left and right counts and their gaps, and then they also have their references to their sister nodes in the predicate tree. Let's do the update and see what happens. We insert the run item into the to-dos list just like we've been doing all along. When this happens, the predicate tree finds out and starts to insert the run item into the tree. Now the run item currently inside of the to-dos list has an index of 3. The skip item in the predicate tree has an index of 1. We were able to calculate that based on its left count and its gap count. We're going to compare those indexes, and we're going to say, okay, run has an index of 3, we have an index of 1, we need to traverse downward to the right. So run is now compared against the jump node. Because we have a reference to our parent, the jump node can calculate, my parent has a left count of 1. My parent represents one node in space, and I'm the node after it, so I must be in the number 2 index position, right? So the run being in the 3rd index, jump being in the 2nd index, we can continue to insert to the right. And that's what happens. The run item in the to-dos list winds up being a run node in the predicate tree. And you can see that we got the predicate result here. This is going to be a truthy. We do want this in the filtered list. Our left count, our right count, and our gap count are 0 because it's very lonely down there in the bottom corner of that tree. But that's okay. So now that the predicate tree has been updated, the completed tree is going to catch wind of it. And it's going to say, well, I probably need to put this in my tree. Let's see what the predicate result was. The predicate result here was true. And so we take the index of the run node in the predicate tree, which we've calculated as 3, and we compare it against the calculated index of the jump node in the completed tree, and we have 3 versus 2. But this is actually a little more clever than it looks, because we have the reference to the sister node in the predicate tree, right? So we're using not the index of jump in the completed tree, we're using the index of jump in the predicate tree while we're traversing the completed tree. So it's like we're going to make the operations on the completed tree, but the logic that we're using to base our actions is actually coming from the predicate tree. We're making decisions about how we're going to interact with the completed tree based on things outside of the scope of the completed tree, which is kind of cool. So let's try this one more time. I want to make sure I get this across. The jump node in the completed tree has a reference to the sister element in the predicate tree. That's the one whose index we really care about, right? So we want to put run in the completed tree relative to where it belongs in the to-dos list. We can't put it before jump, we can't put it before skip, or we can't put it before hop. So when we compare the run node to the jump node in the completed tree, the jump node currently thinks it's in the 1st position. But we know better, it's actually in the 2nd position. So that's why we refer to the predicate tree. And that's why the predicate tree's sole responsibility is to maintain the same order as the to-dos list. And you may ask, like, that seems unnecessary. Like, why would you just duplicate all this data? We already know that jump is the 2nd item in the to-dos list. Except you don't actually know that. And the best way to solve for it is actually in this tree, where we can just kind of keep crawling up the binary tree and recalculating all these left counts and gap counts. It's much faster than like starting on one end, iterating towards your item, finding the item and saying, we kept track of our index, and that's called an index of implementation. So, all right, so we can put our run node into the completed tree. That's exciting. And then knowing that the run node was added into the completed tree at the second index, we can very efficiently say, hey, add one DOM node to the node list in DOM land. So let's take a look at a demo. Oh, I've got a, maybe I should mirror. Let's do this. Excellent. Okay, cool. You guys can see this. We'll start this over. So this is an example of a source list on the far left. It's made up of a couple of items with some random numbers generated. And then on the right, or from there on, every one of these is a filtered variation of this source list. So the first one is all even items from the source list. Second is all odd items from the source list. The third is all items less than 50 from the source list. And then the fourth is all items greater than 50 from the source list. So if we remember our original example, in order to solve for this, we'd have to call filter 4 times, which means we'd have to iterate source 4 times, which means we'd have to go do some pretty clunky DOM manipulation 4 times for every change that happens to the source. So if I were to do this, we would notice an item was added, calculate, calculate even, calculate, calculate odd, so on and so forth. But because of the binary trees, it's really super efficient. Like we said earlier, logarithmic. So I can do something like this, and we notice no lag at all. That was really fast, right? And I can keep doing this. Watch the dots count at the top, which is going to go and go and go. And we can kind of see my repaint rate at the bottom. It's doing pretty good. Now we will see a drop off just because the cost of the repaints is, going to get greater and greater as more DOM nodes are added. But we know for sure that on the JavaScript side, we're not taking an exorbitant amount of extra time to accomplish the task. Also, we can randomize all the items in the list. Just jam on that, and this is filtering over and over and over and over and over again. Every single time we change a number on the left list, it's filtering. And that would typically be really expensive, but it's not anymore. Let's go to React. This is React sorting the same kind of lists, right? We've got the source list, even, odd, less than 50, greater than 50. I forget how many nodes we have here. Yeah, it's 100 nodes. Okay, cool. So let's bounce this up to 1,000 nodes. So let's scroll. So you can see React's chugging through this list, and it's changing every one of the numbers. And we can't really see it. It's not outside the screen, but the filtered lists that are based on or that are derived from that source list are updating. Removing items from them, adding items back in, removing items, adding items, removing items. And it's using our native array filter in order to accomplish that, right? It's doing a pretty good job. Here's can derive, the project that I've been working on, doing the exact same thing. It's managing to do it at 50 frames a second, though, which is a whole lot cooler. Let's go back to React. This is 30 frames a second. This is 50 frames a second. Here's what happens when we take the DOM out of the equation. We're just going to not display any of these items. I'll need to cache them a little bit here. Why aren't they hiding? Oh. I'm not thinking, that's why. Okay, now the DOM nodes are actually being influenced, but they're not being repainted on the screen. So this is happening really fast. If you guys can't see it, it's like 120 frames a second, something like that, or 120 operations a second. React doing the exact same thing. Unfortunately, it's limited by how fast dot filter can chug through those items, and it really can't go any faster. Even though the renderer is like, really intelligent and can make a lot of smart decisions, the filtering is what's going to slow it down. It can't go any faster. It still has to go through 1,000 items 4 times every single time there's a change. And then having to do that means that items are going to be added or removed from the DOM, so on and so forth. So this is the project I've been working on for 6 months. That's all I have to present for you. If you guys have questions, I'd love to hear them. It's something I'm really excited about. Hopefully I'm going to be releasing it soon if you want to take a look at it. It's in a repo called can_derive. The reason it's built on top of can is because we want to be able to observe lists and maps. And then also the objective for the can_derive project is not specifically just to filter lists. The goal is to make it super efficient to update all sorts of data transforms. So maps, group by, and even sorting, which is a whole other conversation. But anyway, thanks a lot, guys. I appreciate you coming and taking the time. Have a good one.